Hi, this is RCC structural design classes with respect to practical approach. Today, I'm going to explain the basics of the RCC structure. Any designs of RCC shall be based on these basics only. I'm an MTech structural engineer. I will be helping out in understanding the RCC topics from the basics at as easy as possible for you. See, there are two kinds of structures. When it comes to structures, we have framed structures, load bearing structures. We have two kinds of structures. When it comes to framed structures, we do design of columns, beams, footing, slabs, everything. These are called frame structures. Frames in sense, beam, column are called the frames. When it comes to load bearing, there will be no beam. All the loads coming from the structure will be transferred through the walls to the foundation or to the soil, to the earth directly. There will be no beam action, there will be no footing, there will be no column action. Complete the load bearing structures will be based on the load transformation of the wall. When it comes to design of a structure, we need to go from the basics. Let's understand the basics. Concrete plus steel is called RCC, reinforced cement concrete, right? Why do you embed steel, or why do you reinforce the steel with the concrete? See, we know that concrete is a brittle material and steel is a ductile material. This is brittle, right? And this one is a ductile one. This is good in compression while this is good in tension. We know this. What is a brittle material? Anything which is broken at sudden, collapses at sudden. If for example you can take a glass, it will be break on an impact. When the impact of the load is applied on a glass, it will be break. So when it comes to ductile, these are good in tension forces. These will reach an yield point before failure. Okay, so these will reach an yield point. So when it comes to concrete, we do reinforce the steel with the concrete because concrete is a brittle one, steel is a tensile or a ductile one. When you combine this, we get we'll design in such a way that if the concrete gets failed, it should be in a it should be failed in a steel manner, so it will be failing in a yield point, so that whenever the yield point of that steel is reached, that concrete starts failing. We don't get any brittle kind of failure in the RCC. Because of that, we'll reinforce the steel. Why only steel? We can go for any other kind of metals, right? Why only steel? Because thermal expansion of steel and concrete are almost equal. Whenever two materials combine whenever two materials combine, if it's a beam in a concrete and steel, whenever two metals combine, there might be a cracks because of different kind of materials. Why does that crack appear? Because of weathering. weathering. So in this, because of weathering, both material will expand and contract, right? Because concrete and steel has almost same thermal expansion and contraction capacity, we do reinforce the steel with the concrete so that the cracks developed because of different material are minimal. That's why we use steel as a reinforcement. Okay, when let's after this, if you go for a design concept, we have a limit state. We use this design, right? We use this one. Another two, we have working stress, working stress method, and ultimate limit method. Okay, we are not going to talk about this now. When it comes to working stress method, we'll explain this one first. FOS, that means the factor of safety. This is the term we need throughout our life. For civil engineers or structural engineers, we take care of this one throughout our life, right? So for this design based on the working stress method, factor of safety is very high, very high. That means in turn will increase the cost, because as the factor of safety increases, my size of the column, size of the beam, size of the foundation, everything will goes high. So this will never fail in in kind of working stress method will never fail, because we consider very high factor of safety. But when it comes to cost, it will be very high. But even though we use this one, right, why do we use in kind of public buildings, such as, for example, if you take a dam, right? For the construction of a dam, you cannot look for cost, so that you can save some money to get to save some money. You cannot construct some low quality, low factor of safety dam, because dam is a very important structure, right? In that condition, we go for the working stress method, where economy doesn't play major role, safety plays major role, right? So in that cases, we'll go for the working stress method. When it comes to limit state method, for example, for structures like residential or commercial or high rise structures, investors look for economy as well as purpose. That means my building, right? So in that case, we go for the limit state method, where the limit state of serviceability will be good, and economy will also be considered. So when it comes to limit state design, we have under reinforced, balanced, over reinforced. Many might think, so if you give it more steel, it is good for our structure, so that we can go for the over reinforced structure. No, that's absolutely wrong. Providing the steel greater than the requirement might lead to disastrous failures. For example, any beams. See, I'll explain the concept of this under reinforced, so that you can judge what's a logic behind this one. When it comes to this balanced section, this is in hypothetical condition. This achieving this is very, and it's not possible easily, because it's in hypothetical condition to for the loads acting, or for the exact loads of acting, so that it will be balanced loads and acting on the structure, and loads resisting by the structure is equal. This is very hypothetical condition, where this is achieving this one is very much dangerous as well as not possible. So when it comes to under reinforced, we give the steel in under reinforced steel we provided is less compared to over reinforced, because when if the if this is the beam, if and it's concrete, and we provide a steel, when if the load is acting here, if the beam is going to fail because of less reinforcement, what happens? It will give a crack for me. Under reinforced in sense, the beam will fail because there is a less steel in this beam. So that means these cracks are developed. I get a warning sign. I may vacate the building, or I may I may do some retrofitting works for this beam to take care of my structure, right? What if it's over reinforced? If the steel provided is very much high, there might be chances that this beam would not have failed in this steel criteria. It would have been failed in the concrete criteria, where concrete is a brittle material. We get a sudden collapse. We do not get any warning sign, right? No warnings are given in case of collapse or sudden disastrous failure or catastrophic failure. We call it as a catastrophic failure, right? So in such cases, we engineers prefer the failure mechanism as a steel medium only. We design in such a way, in either way we can say, we engineers decide the failure criteria of a structure. We if the steel if the beam fails, we define the medium or type of the failure in that beam, right? That's called the under reinforcing. So that doesn't mean that you need to give less quantity of steel. By you will be designing for a steel of 100 kilonewton, right? Example, it will sustain, that's fine. If by any chance, if by any worst condition, if this increases, and you will be having a factor of safety on 1.5, so that it will be sustaining up to 150 kilonewton as well. By any chance, if this goes for 300 kilonewton, then this beam should show the warnings before the failure. I'm giving an example like 300. It might be because of serviceability, like durability, or all the conditions, considering all the criteria. That beam, we define that beam should fail in, if it fails, it should fail in a ductile mode only. Should not fail in a brittle mode. That's what we see in the limit state method of a under reinforced section. Okay, if we design it as a over reinforced section, the steel will be good. That means the required steel to resist the 300 kilonewton, that will be fine. But how about the concrete, right? Concrete will fail for this 300 kilonewton, so that it will give a catastrophic failure. But if you give the less steel before reaching 300 kilonewton, it will give me a warning sign of crack, so that I can able to witness these warnings and take care of the structure. That's the main agenda behind the under reinforced section. Moreover, while designing, we take care of all the structures like factor of safety, right? What's the factor of safety we consider for concrete? For concrete, factor of safety for concrete is 1.5. For steel, it's 1.15. This is factor of safety for materials. Make a note of this. This is for material. For loadings, again factor of safety is considered as 1.5 for in limit state method. Okay, how do we explain that one? We can see a concrete of 150 meter cube. This is the standard uh, procedure. If a concrete of M20 grade concrete casted in 150 mm, 150 mm and 150 mm, right, and it's cured for 28 days, it is achieved 20 newton per mm square. It's achieved 20 newton per mm square. When but this dimensions is not sufficient, but it may not be true for a beam of length 3 meter 4 meter of different shape or curved beam, right? So this may not satisfy. Because of this size we are getting 20 newton per mm square, but this may not be true for this practically, right? Because of a shape factor. Also, as the shape factor increases, there might be chances of increasing the voids, which may result in decreasing strength, right? So for M20, FCK is 20, right? Because of that shape factor, this FCK 33% of strength will is reduced. That means we'll take it as we'll reduce this 33% of strength, or we'll consider this 33% of strength is lost because of this shape factor. So how much we get? So 0.67 FCK will be getting 0.67 FCK. For this one we'll be applying the factor of safety, that will be 0.446 FCK, that is approximately equals to 0.45 FCK, right? So this is how we arrive at the 0.45 FCK in the design factor. When it comes to steel, directly its the strength of a steel is denoted by Fy, and the factor of safety for this is 1.15. As the steels are prepared at the factories, we get higher accuracy for strength, so the factor of safety is 1.15, whereas for concrete it is prepared at the site, so that we'll taking higher factor of safety. Here it is, as it is prepared at the factories, we get more accuracy, so we factor of safety is considered as 1.15. So the strength of the steel is considered as 0.487 Fy, right? These are the basics we need to take care of the structural design. These will help out in the structural understanding the concepts of structural design. Okay, so while designing the structures, we take care of all these factors. We have still many more. We look forward in the upcoming videos. We design a steel we design a concrete structure. So we'll design a beam, column, footing, slab, everything. And also when it comes to practical approach, if a slab with an opening is to be designed, how do we design? Is there any criteria for this? Is there any guidelines for this? Yes, we do have. How do we design these things? We need to take care of all this in upcoming videos. We can learn the all kinds of design, as well as site oriented or practical oriented designs, such as opening the slabs, or a design of a floating columns, or design of a transfer girders. So we will go from the basics, right? These basics are very necessary All the other basics shall be explained in the further coming videos. Hope you understood the concepts. For any doubts and clarification, do comment.